Good afternoon. Welcome from a sunny but cold Paris. My name is Marc Bourgeois and I work at the EUROCONTROL Innovation Hub, and I'll be your host for this last session in the track on complexity, analytics, and big data for ATM. Since we start a few minutes late, I will not dwell any further and introduce our first speaker. Our first speaker is Ramon Dalmow, who is a colleague from me here in Paris. And he has a background, a master's degree in computational and applied mathematics from the Autonomous University of Barcelona, followed by his PhD in aerospace engineering from the Technical University of Catalonia. His research interests are in optimization algorithms, machine learning, and multi-agent reinforcement learning, all of them to improve air traffic management systems. And today, Ramon is going to talk about early detection of night curfew infringements. The floor is yours, Ramon.
Thank you, Mark, for the introduction. I'm trying to share the screen. Okay. Can you see the slides?
Go ahead.
Excellent. So yesterday, I presented the results of one of the projects that we executed during the first wave of InnoLabs at the EUROCONTROL Innovation Hub. Today, I am going to present the results of another project, which the objective was to predict the delay propagation along the sequence of flights of a given aircraft, and then assess the risk of night curfew infringement. But first of all, I would like to acknowledge all my co-authors, Giuseppe, Yves, Ricardo, and Alan, because despite working in very difficult conditions due to the pandemic, we made a great virtual team and the integration went really smoothly. So let's start. This is the outline of the presentation. I will start by introducing delay propagation and also what are the night curfews. Then I will present the model that we train with historical data in order to predict the delay propagation and assess the risk of night curfew infringements. Then I will present the input features or the predictors that the model uses in order to predict the delay propagation. And then some initial results from 3 validation exercises. And finally, some conclusions and future work. Night curfews are environmental restrictions applied at some airports, which prohibit operations during certain hours of the night. For instance, at Paris-Orly, operations are forbidden between 11:30 in the night and 6 a.m. These restrictions effectively reduce the noise in the communities near the airport, but they may also cause negative operational and also economic impact for the airport and for the airline, especially due to the EU 261 compensation, which offers legal protection to the travelers in the event of a flight delay or a cancellation. Night curfew infringements are mainly caused by delay propagation along the sequence of flights that an aircraft is operating during the day. Therefore, if we were able to predict the delay propagation, we would be also able to assess the risk of night curfew infringement. But when we talk about delay, however, we are not talking about a scalar value, a number. We are talking about a probability distribution. Otherwise, the risk becomes a binary prediction, either yes or not. And we are looking for a probability. But we will see this later. This slide shows the mirror HMI, in particular the demand at 11 UTC for Paris-Orly late evening arrivals on the 13th of July of 2019. Mirror is a decision support tool created by EUROCONTROL that helps the operational stakeholders to predict and mitigate the delays. And it's also the tool where the neural network that I'm going to present in the following slides has been integrated. Each row of this display corresponds to a different aircraft, that is to a different tail number. And for each flight, the sequence, for each aircraft, the sequence of flights that has operated is operating and is going to operate until the end of the day is shown as a Gantt diagram. Furthermore, for each flight, we see both the schedule and also the tactical, real-time, and up-to-date situation. So each one of these green boxes that you see in this slide corresponds to a flight, and we can compare the schedule with the tactical situation. And finally, the dashed region that you see in the right corresponds to the night curfew at Paris-Orly. For instance, this aircraft inside the red box is going to fly from Paris to, I think it's Dubrovnik, and then again from Dubrovnik to Paris, Orly. But we can observe that the second leg has an ATM delay, which is the orange region, that has delayed this flight quite a lot. And of course, this is not realistic because, as you can see, this flight plan and the next flight plan overlap. So the idea is to develop, to train a neural network that can predict the delay propagation and push the latest flight and see the probability that it will infringe the night curfew. So this slide shows the result of calling the model in this particular scenario. As you can see, the model identified that the sequence was not realistic because the two flight plans were overlapping. And therefore, the model predicted that some delay would be propagated to the last flight of the sequence. This flight would depart late from Dubrovnik and would also arrive late to Paris-Orly, most probably infringing the night curfew that is imposed at this airport, provided that no mitigation action is performed by the airline, of course. The idea is to perform this prediction with sufficient look-ahead time, such that the airspace user has time to take actions and mitigate the delay propagation in order to avoid the night curfew infringement. For instance, by performing an aircraft swap. Yet, the earlier we make the prediction, the more uncertain the input data and the less reliable the prediction of the model. Accordingly, there is a trade-off between the accuracy of the prediction and the look-ahead time. The model that we develop in this project predicts the delay propagation along the sequence of flights of a particular aircraft. That is along one row of this grand diagram. And for this reason, the input of the model is a sequence of vectors, where each vector corresponds to one flight in the sequence, that is to one of the green boxes in this Gantt diagram. For each flight, the corresponding vector includes the most up-to-date information at the moment of performing the prediction, like the ATM delay, for instance, the departure destination, etc. Well, all the data that you can see in this Gantt diagram. Note that some flights may be already terminated, some of them may be airborne, and of course, at least the last one is still on ground. The sequence of data that we feed to the model includes all flights that this aircraft has operated or is going to operate during the day, even those terminated or airborne. And we just inform the model, as you will see later, about their status. Then, given the input sequence, we can compute a set of features or predictors, like the available turnaround time of each flight, for instance. And finally, we call the model, which is based on recurrent neural networks. The output of the model is the predicted delay distribution for the very last flight in the sequence. And for the sake of simplicity, we model the delay by using a normal distribution. Therefore, the model predicts two values: the expected value, or the mean of the delay, and also the standard deviation, which is always positive. Then, if we add this delay distribution to the scheduled in-block time, as you can see in this figure, we obtain the predicted distribution of in-block times. Finally, if we know the starting time of the curfew period, which is publicly available, we can compute the risk or probability of the night curfew infringement, which is the area under the curve, as you can see in this slide. This computation can be done analytically. The model is based on recurrent neural networks. And for those not familiar with machine learning, recurrent neural networks is a special architecture very good at learning patterns from sequential data. In this case, a sequence of flights. There are several types of recurrent neural networks, and in this paper we use the GRU. Let's start with an initial hidden state that we call H0, And at every step of the input sequence, the operations shown in this slide are performed in order to update this hidden state. The update gate, which is Z, controls the extent to which the information of the previous hidden state is transferred to the current hidden state. And the reset gate, the R, controls how much of the previous state contributes to the new candidate state that we call N. This architecture effectively allows to control the flow of information or of hidden state along the sequence, determining how much of the hidden state is propagated to the next step and how to update the hidden state based on the inputs. Note that if we replace the word hidden state by distribution of delay and input by flight attributes in the previous explanation, one could already guess the working principle of this model. Let's consider an aircraft that for which we want to predict the delay distribution. And we know the sequence of flights that will perform along the day, ordered by off-block time. And any time during the day, each flight of the sequence can be described by a vector of features that we call X that represent its most up-to-date state. Furthermore, this aircraft has some static information, some characteristics that are identical to all the flights in the sequence, such as the aircraft type. And we capture all this static or common information in the vector of static features or context vector, what we call the C. The main component of the model consists of a bidirectional GRU that generates a sequence of hidden states using the sequence of flight features. For each one of these hidden state vectors, that is, for each flight in the sequence, the model predicts the expected value and also the standard deviation of the delay. However, in this project, we are only interested in the very last one, the last flight in the sequence, the one that could infringe the night curfew. Then the initial hidden state of the forward and the backward GRUs are conditioned on the context vector by using two different feed-forward neural networks. The weights of the previous model are trained to minimize the negative log likelihood. Let's imagine that the model predicts the distribution of the arrival delay of a given flight in the sequence. Okay. Actually, the model predicts the expected value, so the mean and the standard deviation, and then we can construct this distribution, as you can see in this slide. But this is just a prediction. Now we need to compare this predicted delay distribution with the actual value of the delay in order to check how good or bad the prediction was and penalize the model accordingly. But the actual delay is not a distribution, it's just a value, a scalar that we know from the past, from historical data. So we can simply check the likelihood of the actual delay in the predicted distribution according to the model, which value is between 0 and 1. If this value is really small, this means that the model predicted that the actual delay was very unlikely, and this is not good. Then we can compute the logarithm of this probability, because the logarithm of a very small number is a very negative number. And however, we want to minimize the loss function, and this is why we take the negative value of the log likelihood. In this way, we are adjusting the weights of the model of the neural network to maximize the likelihood of the actual delay, of the historical delay. It should be noted that in the loss function, we are only considering non-terminated flights because there is nothing to predict for a terminated flight. We already know the actual delay from the historical data. For each flight in the sequence that we use to predict the final delay distribution, the following features are computed, which can be divided in two categories: categorical features, which take discrete values, and numerical features that take continuous values. For instance, in the categorical features, we have the departure airport or the destination airport, and also the flight state that could be terminated, airborne, regulated, on ground, and also the airline, and many others that you can find in the paper. But all these categorical features are represented typically as strings, and we cannot use strings to make computations. So we need to convert them to numbers. And for this reason, we are using a numerical embedding layer for each one of these categorical features, which transforms the string into a vector of numbers, according to some weights, some parameters that we need to learn during the training process. Then for the numerical features, we have information like the turnaround time, the departure delay, the taxi time, the time since the last flight update, so how old the data is for this flight. Also the time to the scheduled in-block time, which is the look-ahead time of the prediction, could be negative if the flight has already terminated. And also the current air traffic flow management delay, if any. Some of these numerical features present a very skewed distribution, which is not good for neural networks. They prefer nice Gaussian distribution, and this is why we perform a power transformation and then a classical standardization in these numerical features. But these are features specific to each one of the flights in the sequence. In other words, they are computed independently for each one of the flights. There are some characteristics of the sequence that are common to all the flights because they are operated by the same aircraft. And these characteristics are used to condition the neural network with the context vector, C. Remember that C is used to condition the neural network by using the initial hidden states of the two directions of the GRU. Once again, this context vector can include categorical features and also numerical features. For the categorical features, we have only the aircraft type, that could be A320, Boeing 737, etc. And that we also fit into a numerical embedding layer in order to transform this string into a vector of numbers that can be used by the neural network to make computations. And this transformation depends on some weights that are also learned during the training process. Then for the numerical features in the context vector, we have the hour of the day of the week, and the month of the year when we trigger the prediction. So when we call the model, and of course, this is common to all the flights in the sequence. And for each one of these numerical features, we perform a cyclic transformation. So we convert each one of these features in two features by computing the cosinus and the sinus. And in this way, we convert them to numbers. The sequence of vectors and the context vectors have been generated by combining two sources of data. First of all, enhanced tactical flow management system data. That this data is obtained per flight. So for each flight, we can obtain several messages. Messages are sent very frequently from the submission of the initial flight plan to the termination of the flight. And one message for each flight is triggered whenever the flight data are updated. So for instance, if the flight updates the ATFM delay or the EOBT or the flight status, we receive a new message in the ATFMS. Okay. And this data includes the departure and destination airport, so very basic features like also the airline, but also some specific features that are dynamic, like the estimated off-block time, the taxi time, the ATFM delay, and also, of course, the tail number, the aircraft that we use to generate the sequences. And another source of data were the airline schedules. And in this case, this data is also per flight, but this data do not change with time and includes the scheduled in-block time and the scheduled off-block time. And we merge all these data sets in order to build the features that I presented in the previous two slides for the sequence of vectors and for the context vector. The model was trained on 280 random days of 2019. And then we used 20 days for validation, which means for fine-tuning the hyperparameters and for early stopping. And then we perform 3 different validation exercises that I will present in the following slides. For each one of the aircraft, that is for each sequence of flights, we took several snapshots in order to generate the examples for training the model, validating, and also for assessing its performance on unseen data. And we took a snapshot whenever one of the flights in the sequence submits the initial flight plan, takes off, is suspended, lands, or is allocated with a new ATFM slot. In the case, the flight is regulated. So whenever one of these events happen, we take a snapshot, and this represents a new example for the model. The model has around 2.5 million of parameters, and in order to train them with a NVIDIA GTX 960, we need around 6 hours, which is not a lot. This slide shows an example to illustrate how the model could be used in real-life operations. Each region of the vertical axis shows a different call, a different prediction of the model, ordered in temporal order from the top to the bottom. The bold numbers in the left show the remaining hours until the start of the curfew. So 15, 12, 9, and the risk of the curfew infringement as predicted by the model. The crosses and the solid dots represent the scheduled and the actual in-block times, respectively, for each one of the flights in the sequence. And note that these markers are static. They do not change between the different calls. Then the vertical dashed lines do change because they represent the most recent prediction of the ETFMS, so the baseline, the current predictions, when calling the model. And finally, the distributions that you see are the predictions performed by the model. And the horizontal axis represent the relative time from in-block time to the start time of the curfew. We see that the first prediction was performed around 15 hours before the start time of the restriction, right before the departure of the last flight, which actually, the first flight, which actual delay was around 30 minutes. Given the short look-ahead time of the prediction, the model was able to provide a very accurate and certain prediction. You see the small standard deviation for the first leg. And note that at that time, the prediction of the ETFMS were excellent for the two first flights. But however, the ETFMS missed the delay propagation to the third flight and the subsequent flights, which was the cause of the night curfew infringement. Note that despite having 6 flights ahead and performing the prediction 15 hours before the starting time of the restriction, the proposed model was able to predict the potential delay propagation, resulting in a night curfew infringement probability of 94%. This slide shows the mean absolute error or the arrival delay predictions for the last flight of the sequence. That is, for the one for which the curfew infringement is assessed. As a function of the time to SOBT in the horizontal axis and as a function of the number of flights ahead in the vertical axis. Here, 0 means that at the moment of performing the prediction, the next flight in the sequence is the last one, the one for which we want to assess the risk of night curfew infringement. The result in this slide were obtained for 60 random days of 2019, not shown to the model during the training process. And the value that you see in each cell is computed by comparing the actual delay of the flight and the expected value of the predicted delay distribution of each one of the samples, and then computing the average. And this is why we have the mean absolute error. As expected, the performance of the model typically decreases as the number of flight legs ahead and the time to the scheduled block time increase. It should be noted, however, that the number of samples in each cell may be different, and they are different. Thus, comparing the performance of different cells may not be fair. But in any case, the prediction of the model ranges from 9 minutes to 18 minutes in absolute error terms. And the relative benefit with respect to the ETFMS predictions, which you can see in the right plot, ranges from 13% to 46%, depending on the look-ahead time of the prediction and the number of flight legs ahead. This slide shows exactly the same result, so the mean absolute error of the arrival delay predictions for all the sequences that were operated from June to December in 2018. But it should be noted that the model was trained on 280 random days of 2019, and therefore has never seen flight data from 2018. Interestingly, the performance of the model evaluated in these 7 months of traffic data from the past is very similar to that shown in the previous slide, which is a very good indicator of the ability of the model to learn the general mechanisms of delay propagation along the sequence of flights of a given aircraft, independently of the year. Of course, as long as the traffic situation is nominal, as I will discuss in the next slide. Again, we can observe that in the region of interest for the airline, let's say between 2 and 3 hours or more before the SOBT of the last flight, the benefits range between 11% and 36%. And finally, assessing the performance of the model on the most recent traffic is very interesting. However, the traffic demand during 2020 was exceptionally low due to the lockdown caused by the COVID crisis. But despite reducing the data available for performing any kind of analysis, such a typical situation also enabled a very peculiar validation exercise to assess the performance of the model on a traffic situation completely different to that used during the training process. This slide shows the mean absolute error of the arrival delay predictions for all the sequences that were operated from January to May 2020, so during the COVID period. And by comparing these results with those presented in 2018 and 2019, we can observe that the performance difference is not significant in terms of mean absolute terms if we look at the plot in the left. However, the figure in the right shows that the relative benefits during this time period were significantly lower if compared to those of 2018 and 2019. The reason is that, on the one hand, the performance of the ETFMS was much better during 2020 due to the low number of ATFM regulations, reactionary delays, and unexpected events. And on the other hand, the model was trained on a nominal traffic situation where the distribution of delays and their consequences on the subsequent flight legs were completely different. So, as a conclusion, we propose a model that propagates the delay along the sequence of flights that an aircraft is going to operate during the day. And in fact, the distribution of delays for the last flight in the sequence in this particular project is used to assess the risk of night curfew infringement in probabilistic terms. This model has around 2.5 million of parameters, and we need around 6 hours to train it by using historical data, but without hard-coded rules, just by feeding data to the model and showing plenty of examples. The initial results from these 3 validation exercises, so past data from 2018, the data of more or less the same year that was used for training, and also data from 2020, from the COVID period, demonstrates that the model can improve the predictions if compared to the ETFMS around 10 to 40%. The architecture of the model, and this is for future work, could be enhanced by considering a 2-dimensional recurrent neural network, in which the hidden state does not only propagate along flights, but also along time, because so far our model considers each one of the snapshots, examples for a given aircraft, that is different sequences, but from the same aircraft, the same day, completely independent. And this, of course, is not true. And maybe a model that considers this time dependence between sequences of the same aircraft could improve the performance. Another natural extension of this model could be to consider explicitly, because maybe implicitly it's learning some things, because at the end it's a black box, external factors such as the weather. We could include, for instance, data from METARs at the different airports in the sequence. And future work should also compare this generic model, because this model is considering all airports of all Europe, with a model tailored to those airports that implement the night curfew. And this is not future work, this is more ongoing, because we are working on this. We are performing a comprehensive study about the future importance, using primary attribution methods like the saliency, the integrated gradients, or input multiplied by gradient, which will help us, hopefully, to identify which are the most important features and analyze the drivers of delay propagation from a data-driven point of view. And that's all. Thank you for your attention, and I will be very happy to reply to your questions.
Thank you very much, Ramon. It was very clear, I think. To all the attendees, so please put your questions in the questions and answers, and I will take the first question from Mark Hansen, who congratulates you on the clarity of the talk. Did you consider simpler models like multiple regression, simple classification models?
No, we did not consider other simpler models because we thought that for the nature of the data, which is a sequence, it's a sequence of flights, recurrent neural networks could work pretty well because they learn if the hidden state needs to propagate to the next step or not. And we consider that this hidden state is the delay. But we could try. Why not? But honestly, I don't know which one of these models could be suitable for a sequential data problem.
So you don't have much hope? Is that what I hear? Well,
we could try, yeah. But here the problem is that we have also plenty of categorical variables, as I explained before, like the departure airport, the destination, that we need to convert to numbers. And we don't know how to convert to numbers. So we let the neural network to learn how to convert to numbers by using this embedding layer. So let's say that from an engineering point of view, it's the easiest approach. Because you just design your model, you feed the data, and you hope that the model will learn something. But of course, this is what we are doing now. We are analyzing the features to really see if what the model is doing makes sense. Because in this presentation, one thing that is missing is the explainability of the model. I am not showing feature importance or why the model took some decisions. And this is really important to see if the model is really learning what it should learn or is just memorizing.
Okay, let's move to the question of Karel Vesely. He has two questions, and the first one, I think you answered a bit in future work. Are you thinking of adding features related to weather or the level of congestion?
Yeah, definitely. I think this could help the model. The question here is why did not use weather features in the design? No? And the answer is that we had only 6 months to perform this project, so we wanted something simpler, a minimum valuable product that we could develop in only 6 months, and this was realistic. Only ATFMS data and schedules. And also from a previous project that I presented, I think in the CESAR Innovation Days 2019 about takeoff time predictions, which at the end was similar because we were predicting the departure delay. Here we're predicting the arrival delay. We observed that the weather features helped, so they were improving the predictions, but were not the major factors. Especially the most important features were the turnaround time and the ATFM delay, and these features are included in this model. But definitely, we must consider them in future work and see if our hypothesis that they don't help a lot, it's true or not.
Now that we're talking about feature importance, I would like to take the question from Nelson Brown, and he's asking, was the airline an important feature?
Yes, it was. I am not presenting in these slides the feature importance, but I can tell you that the initial results that we got by using these primary attribution methods show that the airline is important. Yeah. And also departure and destination airports. So let's say the city pairs in the sequence are really important. But again, the turnaround time, shows to be one of the most important factors of the delay propagation.
Okay, thank you. And I think to conclude, we take the technical question from Karel as the last question. He's asking, how do you determine the target sigma values for the supervision from the historical data?
Actually, there is no sigma in the historical data. We just have the actual delay. And what we are trying to do is we predict the distribution, and then we check the probability of the actual delay in our predicted distribution. Okay, and then we use this as a loss function. But actually, we only have the actual delay. We don't have, as I said before, we don't have a distribution of of targets, no? It's just a value, a scalar.
Okay, thanks again very much, Ramon.
Thank you very much, Mark. Bye-bye.
Bye. And while the next speaker will upload the slides, let me introduce Lu Dai, who is a PhD candidate in transport engineering in Berkeley. And she has a degree with minors in machine learning and statistics and a graduate certificate in applied data science. Her research focuses on data-driven learning algorithms and statistical models to solve real-world problems applied to air traffic management and aviation safety. She's going to talk about having a bad day, predicting high delay days in the national airspace system. Lu, the floor is yours.
Thanks, Mark. Hi, everyone. My name is Lu Dai from UC Berkeley. Today, I'm going to present our FAA-sponsored project on predicting high delay days, aka bad days in the national airspace system. This work is advised by Professor Mark Hansen from UC Berkeley, Professor Michael Bohr, and Professor David Lovell from the University of Maryland. So for today's talk, I will first introduce the background and motivation for predicting bad days, talking about why we want to do it and how we want to do it. And then we go through building the predictive models, including delay metric calculation, feature engineering, and model selection. And finally, we want to discuss some quantitative insights from the model interpretation and conclude our work with future directions. Jumping into the motivation, why do we care about bad days? It not simply means that our system was experiencing high delays on those days. What it really means is the potential opportunities for improvement in our system. And there might be some area that we can improve on those bad days. So for example, traffic flow management like GDP, AFP is usually needed on those days to reduce inefficiency. And thus some work related to bad days could help evaluate the effectiveness of the TFM actions we took in the past, or may also provide some insights for future planning. So with that in mind, the question we have is, given the delay observations and the situational features in the system, can we build a model to learn the relationship between system delay and a wide variety of spatial temporal features? And how do we make use of this predictive model in a way to get some insights from that? So first of all, how we use this model is by taking the prediction results given by the model that could be used to identify the high delay days that are independent of TFM actions taken and examine its trends over time. Because the current observed delays in the system are incorporate some TFM actions. And now this model, after building this model, we will get the prediction results that could help us to identify the high delay days only based on the environment only. Second, the learned ways of the model, when we finally tune and fit on the historical data, can provide some spatial temporal importance of the features and quantify their relative importance in affecting the system delay. And the third aspect is the generalizability of the model, which makes the estimates transferable to a counterfactual context and enable us to make some counterfactual analysis to enhance our understanding of how the system and its environment have changed and affect the system over the past decades. And this property also lays the groundwork for learning the effectiveness of TFM and forecast the delay in the future. In today's talk, we will not be focused on these two applications, but feel free to reach out for more details about our current progress. And today, we will mainly look at how we build such a model to answer all these three aspects of like insights or questions. And so when I say predicting bad days, it sounds like a classification problem with binary labels indicating whether a day is bad or not. But how we actually approach this is by developing a regression model to predict the continuous delay quantity. And then we set a threshold, say 15 minutes or 20 minutes to label a day as a bad or not. So therefore, we first need to define a delay quantity. We compute the delay average arrival delay to compute the daily average arrival delay for formulate the delay variations of the entire system. So this metric is computed based on average positive delay against schedule for all the scheduled arrivals into the core 29 US airports, including completed flights, canceled flights, and diverted flights. We count the flight cancellation as a 2-hour delay and remove all the flight operations with delays greater than 10 hours. And all the flight delays are assigned to days based on their scheduled arrival time. So this is basically our delay matches for each day. And you can see in the figure that its frequency distribution over the past 10 years, basically like 3,600 days here, and with some extreme bad days in the tail. So this is going to be our response variable. And we want to model such delay based on the demand, call rates, terminal states, and the convective weather, wind, traffic volume, special events only. And as I said before, these predictions are going to be independent of TFM actions, and we'll get into the feature engineering in a minute. So this is our data sources that we use. Our analysis has been conducted for the past 10 years, from 2010 to 2019, with all the time zones unified to UTC-10. And the BTS flight level data is used to calculate the response variable that I just introduced, the delay quantity metric. And we obtained the ASPN flight level data, airport quarter level data, quarter hour data, OpsNet data, and the air route traffic control center boundary from FAA. And we also obtained the ground-based convective weather observations, convective forecast, wings aloft data from NOAA, and flight level data from the space launch log from the NASA database. And so this is a considerable amount of data, and we are fortunate to collect all this data set over the past 10 years. Now I'm going to show you how we make use of it to mine some features that might be helpful for delay prediction. The first category is the demand and capacity features. So we employ this cumulative input-output queuing diagram to model the queuing delay due to mismatch of demand and capacity. The x-axis here represents time, and we know the cumulative scheduled arrivals or departures for a given day and airport based on the OAG count in the ASPM dataset. That is like OAG scheduled demand, which is the black curve that we show here in the plot. And we also have the AAR or ADR, which is the call rates specify the number of aircraft an airport can accept from the centers or take off from the airport, also obtained from the ASPN dataset. So by comparing the scheduled arrivals and the call rates, which is less, we can construct the blue output curve here, representing the cumulative capacity constraint arrivals or departures during the day. And when the demand exceeds its capacity, you can see the area between the curves here. And so that is the area represents the queuing delay for all flights arriving or departing on the given day. And furthermore, we believe that the queuing delays at different times of the day affect the system delay differently because of delay propagation. So that's why you can see different colors for these areas that we marked. And so because we break the area into 4 times of the day queuing variables shaded by the different colors in this plot. And it is calculated, so our queuing delay is calculated by division of total queuing delay by the total arrivals during that period across all the 29 airports for a specific time of the day. And our second category of features are from the terminal stage to capture the terminal conditions, because we noticed that airport capacities usually are lower under instrument conditions or windy conditions, but are not fully reflected in the call rates that we use to model these such demand and capacity features. So we derive several features to represent the terminal conditions. The daily, there are the daily proportion of time an airport is under IFR conditions, the change of the runway configurations, either a small change including like open or close a runway, or a big change like flipping the airport. So only if the runway configuration are mutually exclusive between the consecutive quarter hours are considered as the big change of the runway configuration here. And we also discretize the ceiling and visibility into 4 continuous variables based on the criteria for defining LIFR, IFR, MVFR, and VFR. And the third category of features are the convective weather features. So we segment the national space with air rule traffic control centers to capture the spatial effect of the thunderstorm. As the polygon in this plot, the dots here are roughly 3,000 weather stations recording the hourly presence of the thunderstorms. And then we calculate the proportion of weather stations that reporting thunderstorms in each control center. And we also calculate the proportion of area that reporting the thunderstorm forecast in each control center. So the first feature are based on the convective weather observations, but the second kind of features here are focused on the convective weather forecast. And we also have the third features that have the airport specific feature calculating the proportion of flights that's scheduled to land within the thunderstorm period. And this feature, the third feature here, is used to capture the local thunderstorm effect at the airport level. And we also obtain the daily number of military operations from the OPSNet dataset as a proxy for good en route weather conditions, combined with a dummy for the day of the week, since we observe a significant difference in the military operations on different days of the week. And the next category of features are for wind effect. So we decompose the wind aloft data into zonal velocity toward the east and the meridional velocity towards the north, based on the wind directions and the wind speed at 6 different standard pressure levels, which are roughly from flight level 200 to flight level 440. And then at a given pressure level, for example, in this plot, we plot the pressure level at 30,000 feet on a given day, October 25th. We aggregate hundreds of wind observations into one average wind only for each control center, and they are shown as the black wind bars in the map. So the mean absolute velocity, what we are used in the model is the mean absolute velocity and the variation for each center. For each pressure level and the day will be applied as the Wings law feature in our model. And these features are supposed to capture the effect on the ground speed and en route travel time. This is for Wings law feature. And we also have another wind variables, which are the daily average wind speed at each airport to capture the wind effect in the terminal area, where we calculate the headwind, tailwind, and crosswind. So in summary, we have 2 kinds of wind features. One is the Wings law feature to capture the en route travel time effect. And the other one is the terminal wind features to capture some of the effect on the delay. And the last 2 categories features are traffic volumes, and we including the airline scheduled arrivals and the GA operations volumes. And we also have features for special events. For example, we create 4 dummy variables for days with at least 1 space launch event at 4 different US launch sites. And we also made a dummy for Christmas days, since large volumes of holiday travel substantially change the schedules and operations. And we have a dummy variable for different weather forecasting models implemented over the past 10 years in the NOAA dataset. So all these features I just introduced are reproducible and are refined to an airport level or control center level to capture the spatial effects at different times of the day in the system. And they will be used to train machine learning models to predict daily average arrival delay. And these models are fine-tuned using grid search with 5-fold cross-validation. And we pick lasso based on the mean absolute error on the 20% testing set. And we also apply the 5 replicates of 2-fold cross-validation parity test to compare every 2 fine-tuned models and see if their performances are significantly superior or not. And the simpler model, Lasso, is preferred because of its shrinkage and feature selection property. And the model explains 82% of the observed average daily delay variation based on the texting dataset. And it also has good generalizability on the texting set without overfitting. So we apply this train model to predict the daily average delay over the past 10 years. So in this plot, the blue curve is the ground truth delay time series. Though we still have some residuals that cannot be fully explained by the current features, our model prediction, as shown as the golden lines here, is able to capture the dominated pattern as it shows. With the predicted values in yellow, we also can identify bad days by setting a threshold, say 15 minutes, as this red line here. And all those days that above this red line will be labeled as bad days. So looking to more details, we can represent as the bad days as the red square here. And here we have 3,652 tiny rectangles in the Christmas plot, with each rectangle represents 1 day in the past 10 years. So each row represents 1 year from 2010 to 2019. And from the left to right in the monthly order, white days are outlier days, and we remove from the data set. For the 15-minute threshold, there are 1,300 bad days if we're using the 10-minute threshold over the past 10 years. And on the right is the bad day results for the 20-minute threshold. But actually, we are more interested in the trend of the bad days over time. So we extract the yearly percentage of bad days in the bracket and plot the trend here. So overall, as you can see, the orange curve represents the proportion of bad days over that year when we using the 15-minute threshold as the bad day threshold. And the blue curve shows the bad days results for when we using the 20-minute threshold. And overall, we have an increasing trend in the predicted bad days over the past 10 years. And when we're looking at the proportion of bad days over time, and things are getting worse in some sense, except for the 2012 and the 2016. And the percentage of high delay days has almost doubled since 2010, as we currently have in 2019. So the bad days has grown rapidly in recent years. And the second story we want to tell from the model is that how can the delay prediction change on average when a certain effect is eliminated? For example, what if there is no arrival queuing in the system, and what if there are no thunderstorms or no winds? So of course, these scenarios are counterfactual because they are not going to happen in the real world. But through this counterfactual analysis, it can help us to answer like what a certain group of features contribute to our delay prediction. What it means is like feature importance to our in our model. And to answer this question, we set some feature values as 0 to construct these counterfactual scenarios, and use the train model that we developed before to process the new counterfactual feature space and see how the delay prediction will change from the base case. So we compare the relative change of the baseline predicted delay and the counterfactual predicted delay here. So both the delay expectations here are processed using the same model that we built before, but they are having a different feature space. So for the baseline delay prediction, we use the original feature space, which is X here. But for the counterfactual prediction, we have some features that set into 0 to capture their factor contributions. And here are the results. We plot the results as a bar chart for each group of features. The horizontal axis lists the group of features that we change to reduce the system average delay. So for example, what I mean AQD and DQD here is that we assume that what if there are no departure queuing delay or arrival queuing delay in the system. And this bar 26.9% will be the percentage reduction in our delay prediction. So, and this color bar indicates the percentage reduction, and which can be used to interpret our feature importance, and also the rank of the feature importance in general matches our expectations. For example, as I mentioned, the queuing delay if there is no queuing delay in the system, our arrival delay will be reduced by 27%. And also, if you're looking at the ranking, the queuing delay, Southern Strong's, and Ring have the highest impact on reducing the system average delay. And also, we noticed that the arrival queuing delay has a greater delay impact than departure queuing delay for our specific queuing delay matches calculation. And for the thunderstorms, which is the red, which is these 3 red bars here, if there are no thunderstorms in the system, either at regional level or local level, the system arrival delay will drop about 21.5%. And if we're taking out of the effects of surface wind on the terminal and the effects of the wind slope en route, it will result in a 37.6% reduction of the system average delay overall. And as expected, the queuing delay variables may not fully capture the effect of the ceiling, visibility, and meteorological conditions, and also the change of the runway configurations. So if we have ideal visibility and ceiling conditions at the airport, it would trigger about 12% reductions in system delay, even while keeping the queuing delay variable constant. So this story is about the feature importance. And the last question we would like to answer from this model is how the system and its environment have changed and affect the system delay over the past decade. And the answer could be like increasing demand, improvement of aviation facilities, or worsening environment as we have like more thunderstorm nowadays. So basically, we want to explain the trend that we found in the first story, that why we have this trend like this for the bad days. So how we're going to do that is also using the counterfactual analysis. So for example, we asked the question that if the demand in 2019 had not increased from 2010, keeping all other features the same, how would the delay in 2019 have changed? So remember before we set some feature values to 0 to construct the counterfactual scenarios. But here, to answer this question, a different question, we build the counterfactual scenarios by replacing all the demand data in 2019 with the demand data in 2010. So basically, we assume that the demand hasn't been growth for the past decade, and we still have the demand data in 2010. And then with the demand in 2010 and capacity in 2019, we then regenerate the queuing delay features with the 2010 demand, but keep the 2019 capacities the same. And then next, we will apply the chain model to the counterfactual feature matrix to predict the daily system average delay in 2019. And finally, we will compare the counterfactual delay and the predicted delay using the same formula that we calculate the relative change of these two delay predictions. And such difference between these two outcomes would be the impact of that factor. So in this example, we might conclude growing demand in the next system. For the prediction year 2019, we repeat this procedure for different groups of features and using the 2010 features as the counterfactual. And here are the counterfactual analysis results for the 2010 and 2019 year period in this table. So based on the actual 2019 features, the average, so in the original case, we use the original 2019 features, nothing is changed, nothing is counterfactual, and we got the average arrival delay prediction in 2019 was 15.98 minutes per flight. This is our delay metric that we use to model the predictive model. And we also identify 175 days as the high delay days, and using the 15-minute threshold, and we have 80 days when we use the 20-minute threshold. And here we have the percentage change for all these 3 different matches: average delay, bad days 15, and bad days 20. Let's focus on this column today, is that the average delay percentage decrease. So increase or decrease. And so let's look at the second row, which is the demand here, that the cases that we just discussed. So this answers the question that we just want to answer, is that if the demand in 2019 had not increased from 2010, what is the delay in the 2019 would have decreased or increased. So the result shows that if that case happens, our delay in 2019 would have decreased 7.4%. And the number of high delay days divided by 15-minute and 20-minute threshold will have dropped roughly 16% or 13% respectively. And however, if both the demand and the capacity stay the same as they were in 2010, as you can see this row here, if we change both the demand and capacity as the 2010 level, keeping all other features the same, the delay in 2019 only increases 0.23%. What it means is that it tells the story that the capacity just kept up with the demand in the NAS system over the past 10 years. And so this table also shows that the delays for the convective weather, the delays would have 7.11% lower in 2019 if the convective weather in 2019 had been the same as in 2010. So what it means is it also means that the convective weather is changing over time. Maybe it's like worsening. And so that table is only for 1 year period, which is 2010 and 2019, but we don't know anything like happen in the middle, and there might be some chance for that. So we now extend the counterfactual analysis for every pair of the years from 2010 to 2019. So in other words, for every feature of interest, we construct 90 counterfactual scenarios for all the permutations among the 10 years. And that's why you got this plot as a matrix here. So this plot shows the all-year period counterfactual results for the thunderstorm features. The horizontal axis represents the predicted year, which is the year that we want to predict the counterfactual delay. And the vertical axis represents the year whose data are used to construct the counterfactual features. So each cell shows the percentage change in delay as we show in the previous table. Warmer colors indicating delay increase. And what it means is that the year on the horizontal axis is better. And the diagonal cells represents the actual situation without counterfactuals. So there's no change in the prediction. Let's pick one number in the top right corner, which is negative 7.1%. It means that if the thunderstorm events in 2010 had been presented in 2019, the system average delay in 2019 would have decreased 7.1%. So this result is the same as what we obtained in this table, because it represents like we want to have the predicted delay in 2019 using the counterfactual features in 2010. And the whole heat map basically tells the story that worsening convective weather has caused increased delays, especially after 2014, as you can see more red rectangles in the plot. And it also indicates better thunderstorm activities in 2010 from the system perspective. And so this observation shows the results for every year period, although we only plot the thunderstorm matches here, but we also plot such like similar matrices for the demand, capacity, and the wind, etc. And basically the story is that for the queuing delay features, we also observed demand surge in 2013 and caused temporary delay increases, but the capacity subsequently caught up. And the observation explains, that's why it explains a small peak in our 2013 and 2014 in these bad day trends. And also the delay impacts of the year-to-year wing change have been modest and exhibit no clear change. And other features seem to be stable over time with respect to their contributions to flight delay. So basically, through the third story in our analysis, counterfactual analysis, we can explain why we have a surge delay in the 2013 here, and why we have increasing back days after the 2014. This is because convective weather, and this is because we have a surge demand in 2013. So this is all the stories that we want to tell today. And in summary, we apply machine learning techniques to predict flight delays in the national airspace system using spatial temporal features, including queuing delays, terminal conditions, convective weather, wind, traffic volume, and special events. And the feature engineering part is definitely a significant contribution, as it provides some new strategies to derive features that may be helpful for many aviation studies. And we further quantify the importance of each group of features by calculating the percentage change in predicted delay after replacing the feature values. And the rank of the feature importance in general matches our expectation. Like queuing delay, thunderstorm, and wind have the greatest impact on the system average delay. And we then identify the high delay days in the mass with two thresholds. And overall, we observe an increasing trend of high delay days over the 10-year period, with a rapid growth in recent years. And in order to better understand how the system has changed and affect the system delay over the past decade, we answer the third question that by applying a counterfactual analysis to all the 90-year periods, and we observe worsening convective weather, especially after 2014, which explains the rapidly increasing trend in the number of bad days from 2015 to 2019. And we also observed demand surge in 2013, caused the temporary daily increases, but capacity subsequently increased in a similar amount. And so for future work, we know that the model still has some room to improve, but at least for now, the model can satisfy the needs for the current analysis. And it's also possible that model performance could be improved by adding more data or better deal with the feature space. And this work could be extended to like the two applications that I mentioned at the beginning. It can be used to assess the effectiveness of TFM by considering the traffic management actions taken on the predictive high delay days, because our predicted high delay days are identified only by the system environments only, and independent of the TFM actions taken. So if we do a comparative study on these predicted high delays and also the observed high delay, it should provide some meaningful insights into the operational needs of TFM and the improvement of the national airspace system. And the second part is that we can use this model to forecast high delay days in the system in the future using some forecasted features instead of realized features that we are currently using. For example, the demand forecast can be used in our analysis to reconstruct the queuing delay features for delay forecast. And so flight operators would value such predictability to plan their responses further in advance with some knowledge that what traffic management actions were taken on a similar historic day and how well they work. And that's all. Thank you so much. I'm happy to take any questions that you might have.
Thank you very much, Lou. I would commend this paper for its very extensive analysis or description of the data sources and the features, and then the counterfactual analysis, which came very well out in this presentation. Thank you. I have no questions yet from the audience, so please, if you have a question, put it in the Q&A and I will pass it on. Can you go one slide back, please, Lou?
Sure.
I know from the reviewers that the second point was a point of concern. So whatever you conclude is with flow management interactions included in the data set. And I'm not clear how in the future we want to tease that out. It is over the 10 years, the capacity has followed the demand, but has there been a contribution from improved TFM actions? How do you want to find that out?
So this is our currently work for doing that. So this should be the first, second bullet point here, that we have the predictive model to predict the delay that are not involve any TFM actions taken, because we don't have any features for that. We only identify the bad days for the based on the environment variables. So we have a set of bad days that are identified by the environment, but they are not necessarily bad days in our real world observations. So for example, because you have some convective weather on a certain day and our performance is expected to be worse, but because of some good TFM actions taken, actually in real world, we didn't observe high delays on that day, which means that our TFM actions is effective. But for some bad days, we have bad days because of the environment, because of the convective weather and wind, and we take some TFM actions, but we still observe those days as bad days in the system. So by comparing these two set of bad days, like different concept of bad days, we will have some, I expect that we will have some insights about whether the TFM is needed on that day or how effective it is.
Okay, but is there not some hidden effect of TFM actions on the queuing delays? Is there not already something in those features?
Yeah. We expect that like there might be some of the TFM effect that capture in our feature space, but it should be like our average TFM actions that model in the current predictive model is like average TFM actions.
Okay, my second question, while I'm still waiting from contributions from the audience, would be to revert the question Mark Hansen launched for the first presentation, where he was saying, couldn't it have been done with simpler models? I would ask you here, couldn't it have been done with more sophisticated models so that it's more easy to tease out the contribution of the individual features and to have better interpretability? The techniques that Ramon presented, would that they be candidates for this kind of analysis?
Yeah, so as I said, there must be some room for the model improvement. So currently we only take some machine learning models to predict the daily delay. And of course, in the future world, we can like do a more refined levels for hourly delay or maybe a better delay metrics, and also try a more complicated model to model this. Currently, we are trying some machine learning models and to make sure that we have generalizability of the model to do all the counterfactual analysis and to get some interpretation for that.
Thank you very much, Lou. No further questions. I would like to thank you and Ramon again for very clear explanations for not so easy material. And I would also thank Miroslav for the support in the background with this session. This concludes the track, and you now have a coffee break before it continues. Thank you very much.